So let's continue on here looking at the concepts of plasticity, growth, and adaptations. So we talk about the nervous system in terms of its ability to repair and regenerate. There's a lot of changes that take place with aging, which we'll talk about later on. However, we have to first look at what goes on in terms of regeneration and repair. And in this case here, we're talking about the ability for the axon to grow and for the soma to respond to the amount of stress that's being placed upon it based off of establishing new dendrites and making new synaptic connections. We have to make these new connections because we have to remember is that the cell itself will not divide, but what it has to do is it has to generate more connections so as to alleviate some of the stresses that are being placed upon it. Not only is it going to generate new connections, but what ends up happening is that we're going to generate more proteins within the neuron itself, and the axon itself will actually grow as well. We have a limited amount of repair that's able to take place within the central nervous system. However, in the peripheral nervous system, we can go about having regeneration and repair as long as the neural tube stays intact. So let's take a look at how this. So how do we get those changes taking place? It's about what's referred to as axonal transport. The axonal transport is the ability for the neuron itself to move proteins and vesicles from areas of synthesis to other areas within the axon itself or within the neuron itself, in which we have distinct ability to move substances about through what's referred to as axonal flow. There are two types of movements that take place. One is referred to as slow movement. This is movement away from the soma or the cell body. Notice the speed at which this takes place, less than 5 millimeters per day. This takes place due to microtubule or neurotubular and neurofilamental cytoskeletal structural growth. Once that growth takes place, once we have the cytoskeleton laid out, we can then go about using what's referred to as fast axonal flow. Fast axonal flow will go between 200 and 400 millimeters per day. We can transport things both away from the soma as well as towards the soma using a fast flow mechanism. The fast flow mechanism is going to utilize the microtubules and microfilaments, the neurotubules, neurofilaments that were laid out during the slow axonal growth phase. So let's take a look at how these look schematically. So let's start with the slow axonal. And so with slow axonal, what we're doing is that we are building the proteins. We are building the cytoskeletal proteins that then, due to chemoattractant signaling within the axon or within the dendrites, will propel the filaments and propel the microtubules into place. You can think of this as loading the railroad tracks into the projections of the neuron to allow for the movement of materials through the fast passage. In the fast passage, we're going to be moving materials via kinesin and dynein motor proteins. The kinesin and the dynein motor proteins have contractile proteins that function very similar to myosin and actin within the skeletal muscles, where they're going to be walking. I'll show you a crude animation of that here in a second, in which the kinesin molecule will take material antegrade that is away from the soma towards the axon terminals, whereas the dynein will move things retrograde that is from the terminals back to the soma. This is less reliant upon the building of the cytoskeletal proteins and more reliant upon ATP availability and the motor protein availability. When we talk about the movements, we talk about it being a positive, negative movement. Positive is away from the cell body, negative is towards the cell body. The orientation is going to dictate the growth that takes place, whether we have hypertrophication, getting larger, or atrophication, getting smaller within the axon as well as within the dendrites. Most of this is going to be reliant upon the stabilization of the protein structures so as to allow for proper neuronal functioning. So let's take a look and see how this lays out. So watch the protein motor pulling the vesicle along. This protein motor is basically walking along the microtubules. Each time it does that contraction within the motor swing, we're going to be utilizing ATP. This is one of the reasons why we have such a high energetic demand within the nervous system, along with stabilizing of the membrane through the sodium potassium pump. So notice all of these filaments and tubules throughout the axon, stabilizing the axon so that it remains intact due to the various stress and strains that are applied to the axon itself. Takes place. So what we're looking at here is we're looking at the synaptic activity of a neuron. Watch all of the bright spots that are lighting up. Those are all connections that are taking place. Notice as we get more connections taking place, we get a more robust neuron. The neuron is actually sprouting new connection points to take place. Notice how the actual dendrite gets larger here so as to transmit greater amounts of information from each one of those new connection points. Now let's watch what happens in terms of stimulus and then removal of stimulus. And so we're watching here the neuron activity underneath the controlled factor. So notice we get movements of the neuron itself based off of cytoskeletal rearrangements. We're now going to wash it with glutamate. We're going to inhibit some of the regions Notice how we get withdrawal of areas. We're going to excite some of the regions. Notice how we get growth of the axons and terminal branches within those axons. So once again, watch how we will see changes in terms of the robustness of the axon and the number of collateral branches that take place based off of the stimulus versus the removal of the stimulus based off of exposure to the neurotransmitter that's being washed into the area. So once again, watch what happens. We get immediate sprouting based off of the activation. We then remove that activation and notice how we have that immediate atrophication that takes place. This is what occurs all the time with your neurons based off of how those neurons are being used or not used. And it's this use or not use that leads to a lot of the neuroanatomical structural change that we see that takes place.